Okay, let us start. Sorry. So thank you for coming in spite of the terrible weather. So today we are going to continue setting up the path integral formalism, and the problem we will be interested in is many-body problem, where we have some set of identical particles that are interacting. They are subjected to a Hamiltonian that has some single body term and a two body term, and more generally we can generalize it, but to set up the question that we will be interested in is calculating physical quantities and thermodynamic quantities at finite temperature, okay, in general. So, as you know, in general, from statistical physics, what we need to compute to be able to derive all physical quantities is a partition function, right? It's something that its derivative will give us everything we want to know about the system. And of course, the challenge, the technical challenge is how to solve it. But we start from a definition, and we will develop a formalism that is called the coherent state path integral. And the idea is similarly to what we've done last week, which is to use the basis of coordinate and momenta of a particle to describe the time evolution of a particle. Here we are going to use the states that are eigenstates of the annihilation operator of this set of particles. So let us first set up the problem, and today we are going to focus only on bosons. So we have a set of identical particles with bosonic statistics, and they are described by operators that are set of annihilation operators and creation operators. Alphas are some quantum numbers of the single particle states. And these annihilation operators are defined in such a way that they annihilate a vacuum. Okay, so they are defined with respect to a given vacuum, and the Hilbert space of many-body states is can be described in a variety of bases, but one of the most convenient that we learned in the previous lectures is the Fock state, okay, which is a state of...
Just a question, what are the two alpha indices? Like there's one inside the brackets and one outside.
No, this is just to say that alpha goes, I don't know, some counting of...
okay.
It's just an image.
Okay.
Just to say that it's an array.
Okay,
it's an array of operators. Okay.
Okay, I understand.
Okay. Yeah, and the definition of this annihilation is that when you apply A of any alpha on the vacuum, it gives a 0. Okay, and we introduced already the Fock states, which are states with well-defined number of particles, which you can write as, let me denote them generally by some n, where n is an array of occupations, and typically they are of the form product over some set of lambdas, of alphas, of A alpha dagger to the power n alpha, and n alpha is going to be the occupation of each alpha in the state, all that acting on the vacuum. And this is a Fock state. It has well-defined number of particles, which is just the sum over all the n alphas, and the set of all possible Fock states is a basis for the Hilbert space of many-body particles. Okay? And now the main problem is that generally we would like to solve a problem where we have a Hamiltonian, and I'm writing write it like this. So there is a single body part plus two body as a sum of generally four indices, P, alpha, beta, gamma, delta. Okay, something like that. And in principle, you can also have more complicated terms. You can have 3 body, 4 body, 17 body. But notice that I'm writing the Hamiltonian, and this is just a convention, in normal order. Normal order with respect to the vacuum that we defined. I remind you what is a normal order for any operator is a representation of it where all the annihilation operators are to the right. So therefore, when you apply it on the vacuum, you get 0. And therefore, a normal ordered state, normal ordered operator does not have a vacuum expectation value. Okay? Right. So this is just a reminder. Now, what is the problem that we want to solve? We want to compute a partition function where the partition function is defined as a trace over all quantum states of e to the minus beta. Here I'm going to add to the Hamiltonian a term mu minus mu n, a chemical potential term. So what I'm writing, this definition is the grand canonical partition function. You remember this from StatNet? So it is designed to describe a state where the number of particles is not dictated, it's the chemical potential. Okay? So, and it usually for most many-body problems, this is a better ensemble to work with, because in any case, we have in many problems, and especially in interesting problems, we don't necessarily have a well-defined number of particles. They can be created and annihilated. You can have superpositions of states with different particle numbers, right? So this is what we work, and here mu is a chemical potential, as I said, and beta is the inverse of the temperature, which generally we want to keep finite. It's a parameter. And I'm working throughout this class in units where h bar and the Boltzmann factor are 1. Okay, so temperature and energy have the same units. Okay? And frequency, if you like. Okay? Okay. right, so what is the partition function? If we write it more explicitly, what is the definition of a trace? A trace is the sum of all the diagonal terms of some matrix. Okay, so suppose we write our Hamiltonian as a huge matrix in our Hilbert space. Then the trace is simply defined as a sum over n of the diagonal term the diagonal matrix element, where here n is some basis. I don't care what it is. Okay, it is true for any complete basis. All right. How we do this computation? So the main challenge is that we have an operator in the exponential. Okay, and if you write it in, let's say that we take these n's to be some Fock states, we know how to compute expectation values of operators that are single body, maybe 4 operator, maybe 6 operator. It's getting a bit complicated. But an exponential is an infinite sum. If you expand it as a power series, it has many terms, and you have to keep track of the order, becoming messy. So we want to convert it into a path integral formulation in which we will eventually get rid of the operators and replace it by a multi-dimensional integral, and actually an infinite dimensional integral, which is what we call the path integral. So that's the idea, but in order to do it, I remind you what we did in the single particle case. We took this exponential, and we look at this parameter beta as something that we call an imaginary time. It's like a parameter that has units of time. In our units, beta has units of time, right? So if it's a parameter that goes from, you can think of this thing as describing some evolution in the imaginary time axis, which you can break into small steps. And if you break it into small steps, we know that for each step in the limit that it goes to 0, we can neglect commutators. We already discussed it last week. And therefore, we're going to get something that will be replaced by numbers rather than operators. But we have to take the limit that this step size is going to 0. Okay? So this is the idea. That what we want to do is to take this operator, this exponential factor, and write it as a product of many times the same thing. So it's actually okay, and this we're going to do this. There are n terms in this product, and what it means is that we are actually looking at the imaginary time axis that goes from 0 to beta. This is imaginary time, which we denote by tau. And this d tau is the time step. Okay? And each of these exponential describes the evolution within a tiny time step. In the end, we want to take n to infinity, which corresponds to d tau going to 0. And this will give us eventually our path integral.
How are you connecting the d tau to the beta?
So d tau is the size of this tiny interval. Okay.
The beta is not
So
the same
beta,
It's not the same beta as the temperature, right?
it's the inverse. This beta. Okay, again, you can look at this. This exponential is like beta times the operator. Okay. Instead of writing it as beta, I write it as a sum of small interval. When you sum all of them, you get a product of exponent. And again, in the limit that you can take d tau to 0, you get just a product of evolution operators in time, and where tau goes from 0 to beta in intervals of d tau. So d tau is the size of the time step, which eventually we're going to take the limit that it goes to 0. Yeah?
You said that tau is imaginary time.
Tau is imaginary
Yeah,
time.
so-
It's imaginary time. It's a completely mathematical. It's a mathematical construction, but it has the same structure as the real time in problems where instead of this thermodynamic factor, the Boltzmann factor, you have a time evolution e to the minus I h2. Remember, so
Yeah,
that
but-
this is what we do is analytical continuation of this. Maybe don't confuse the T, capital T here was time. So let me just call it a little t. We are doing analytical continuation of this to e to the minus beta h, where beta is identified with minus I.
Yeah, my question was why didn't we write the I, the exponents?
There is no I. It's thermodynamic. It's a Boltzmann factor. It's a Boltzmann factor, right?
What I don't get is that d tau is unitless, right?
No, it has units of time.
Okay, it's a unit of time. And beta has units of one
Time,
over.
of time. H bar and the K bar Boltzmann equal 1. Okay.
Okay.
In those units, so if you would like to bring back the units, then beta is, so this beta actually has to be,
No, it's KBT. KBT is energy. KBT.
that's right.
So it's 1 over energy, 1 over just.
Right, but
which
1
is
over
time.
energy, 1 over energy is 1 over frequency. If h bar equals 1, okay, h bar,
Okay, so we have
okay.
h bar over.
energy,
Okay.
let me write it,
Okay.
okay, has units of, okay,
Okay.
all right? So if I'm taking these to 1, then beta has units of time.
Oh.
And the d tau and tau has units of time. Okay, but it's an imaginary time in the sense that we are relating it to the time evolution by a factor of I, that's all. Okay, and that's why also, okay, yeah, we'll see what we get. We did it last week, but now we're going to repeat the exercise. So the main difference of what I'm going to do today as opposed to last week was that we no longer have a single particle and coordinate and momentum. The building blocks of our theory are now the creation and annihilation operators. And therefore, if I want to play the trick that converts this into an integral, I need to work in a basis of states that are eigenstates of A, the A alphas. And these are the coherent states. So let me remind you. Okay, so okay, if needed, I will bring it back later. So I remind you what are the coherent states. First of all, we have this, I just remind you of the commutators that are big between the operators, and we define a coherent state phi to be such that it's an eigenstate of A alpha for any alpha with an eigenvalue that we denote by phi alpha, and it has to be a complex number, okay? Because A is not a Hermitian operator, and therefore its eigenvalues are some complex number. Okay? So what is the state phi? And we should actually think of it as this notation actually corresponds to a series of numbers. Okay, it has components for each alpha. So explicitly, one can show, and this is something you will prove in your homework, we can write an explicit form of phi in terms of the second quantization operators as an exponential of a sum over alpha, phi alpha, A alpha dagger, active on the vacuum. Okay? This is the coherent state. One can prove that it satisfies this condition. And we also showed last time, yeah, question?
So it's not a clock state, right?
Absolutely. In fact, it is, if you interpret this exponent as a power series, right? It's a Taylor series of an exponential has infinite terms.
So it's some combination.
It's a combination of all possible particle numbers. Okay? That's, by the way, it must be that because it's the only thing that can give you an eigenstate of the annihilation operator, right? Because the annihilation operator will give you 0 if you have finite number of particles, it's you cannot get strictly 0. Sorry, you cannot get an eigenstate because it always reduces the number of particles by 1, right? So in order to have an eigenstate of this, you need something that annihilating one particle doesn't change it, brings it to himself. It's highly non-trivial. Okay? So you can exactly prove this.
If I apply the annihilation over this current state,
you will do it in your homework and prove that you plug in this expression, use the algebra that we know, and you get this. Okay? All right. Now, as I said, phi alpha is complex. So this equation, if I write its Hermitian conjugate, I get the following. So this is the Hermitian conjugate of the left-hand side. And that equals phi alpha bar, where phi alpha bar is the complex conjugate of phi alpha. Okay? And because of that, you can show, and this is also something we already did, if I now look at inner product of two coherent states with different phi's, I get an exponential of a sum of alpha of phi alpha bar, phi alpha prime. Okay? Okay, so you get an exponential of this thing. By the way, let us introduce a shortcut notation.
Shouldn't it be a
yeah.
sum? Why is it a multiple? Shouldn't it be a sum?
What should be a sum?
Because it's two exponents time each other. Why
No, it's not two exponents. It's an exponential of a sum. That's what you get. You have to calculate. It doesn't follow immediately, maybe. But
oh yeah, if you do a Taylor expansion.
Okay. Yeah. Yes. Okay. That's what you get. It's an exponential of a sum. Okay, it's a number. Okay, that's already an inner product. And I want to introduce now a shortcut notation. Maybe I'll write it somewhere here. Let me write it right here because we're going to use it. So I can write like a scalar product in this basis of alphas as this. So this exponent, this thing that appears in the exponent, you can think of it as a scalar product, as a scalar product between two complex numbers. Okay? And because phi, this phi is a vector of all possible alphas. Okay. Great. So this is a general expression for an inner product, but it implies that now if I take phi prime to be equal to phi, a special case of that is that the inner product of phi with itself is not 1, it's actually, I'm just plugging in the same expression, it's e to the sum of alpha by absolute value square. So it's always bigger than 1 because it's an exponential of a positive number. Okay, this thing is again, if I want to use my shortcut notation, it is just phi, it's phi bar phi or right? Okay, so this set of coherent states is over complete because this, in principle, this can be an infinite number also, right? Because the alpha, I mean, it can be, it's some basis of single particle state. It can be a continuum, it can be an infinite sum. So, and it always gives something that is bigger than 1. In fact, it's an you cannot normalize it. It's not an orthonormal basis. It's an over-complete basis. But to compensate for that, you can still work with it for our purposes, but you have to bear in mind that you always have this factor that you cannot just replace by, you cannot just normalize by some constant. Okay? So what you have to do is if I want to write a resolution of the identity in coherent state basis, I have to, by hand, introduce a compensation of this exponential factor. Okay? In other words, when I'm writing a resolution of identity, which usually is for a complete basis, we write it as something like that, right? The sum over all states of the projection. But if this is what this gives the resolution of identity, provided that n is an orthonormal basis. Because actually, what are we doing? Each term in the sum, we are dividing by the inner product n, right? Which is 1. Therefore, I'm not writing it. I don't bother to write it. But if now I have coherent states, I have to introduce this factor. So the resolution of the identity is going to be, let me write it like this, it's a product of all alphas of this is a pi, the 3.1 something, times, and here I want to write phi, the projector, but I'm dividing by the inner product. So it looks like this, right? But this 1 over this is nothing but e to the minus this exponential. Okay? So let me write it more compactly. I first want to introduce a notation. So this differential, which is a multidimensional differential, I'm going to denote it by d of phi bar phi. Okay, this is just a shortcut notation for all this. And under this definition, let me write down here the resolution of the identity. Okay, in this, so it's integral phi bar phi e to the minus sum over alpha phi times phi. Where, just to let us keep this definition here. The definition of this is the product over all alphas of d phi bar d phi alpha divided by a factor of pi. And the factor of pi is to cancel some Gaussian integral factor. Okay? So it's just a normalization factor. Okay, this is the resolution of identity. So which means that we can plug it anywhere we want between two operators, the same tree. This will allow us to sandwich, so if we go back to our Boltzmann factor, which we now write as a product of operators, just like what we did last week, we're going to plug in a resolution of identity in between each of these time steps. Okay? And in each case, it will introduce us some states, and we'll get matrix elements between phi of one time step to the next. Okay? So, okay, so, but before we do it, there is one stage that we have to apply. Notice that in my original definition of the partition function, I wrote the trace in a basis that is some complete basis. I didn't even specify what it is, but it's definitely not the coherent state basis, right? Because the coherent state is not an orthonormal basis, not correct. This is not a correct expression. I want to switch from this to the coherent state basis. How do I do this? Okay, I can do it as follows. Let us, before doing anything else, right? I'm going to introduce the resolution of identity, this resolution of identity somewhere here. Okay? So I'm writing it as this integral over phi bar phi e to the minus phi squared. This is a shortcut notation for the sum over alpha, etc. Of phi. Okay. Now, I can take the sign, integral sign, and this exponential, I can move to the beginning, right? Because they are just numbers, right? I can change the order of the sign and integral. Actually, it doesn't matter. I can take this factor and move it to the beginning. But then I'm going to be left with, let me show you what I get. I'm going to get, I'm writing it explicitly, and d phi bar phi. Actually, you know, let me, just for good measure, sorry about that. I'm going to change the notation from phi to psi. Why? Because I'm going to bring it to a form that is similar to what you find in the books, that's all. So let me just call it psi and not phi. Okay, it's another Greek letter, but same thing. It's some complex, a complex set of numbers. And now I'm taking out this integral over the psi outside and the exponential factor. And then I have the sum over n. And what's left is, let us be careful, I have a sandwich or an inner product of n and psi, right? N psi. Psi e to the minus beta h minus mu n, right? Okay? So nothing, I just introduced the resolution of identity, but why did I do this? Because now notice, in my expression now, I have a matrix element of an operator, it's a number, and this is also a number, just a complex number. Because it's a number, I can switch the order, right? So I can take this and move it here, right? It is allowed, right? It's an interchange between two regular numbers. And then I get the following expression, sum over n, sorry, let me, sum over n. Now I switch the order, so I have this beta h, n psi. Okay, I just switch the order. Okay, nothing more. But now, why? Now I think you see why I do this. So exactly. So I have to be a little careful. This is a projector. So if I take this factor and sum over n, I get 1, right? It's the resolution of identity in the regular representation of Fock state or any orthonormal basis, any complete basis, okay? Therefore, I got rid of the n's, and what I'm left with is just the integral over the psi's. Okay? So this is what I got. And then what I'm left with is I have to, so I'm actually integrating over all the psi's. There is an exponential factor that compensates for the over-completeness. And I have a diagonal matrix element, but now it is in the basis of the coherent states. Okay? So I just transformed the trace into coherent states. Okay? Great, okay. So now what do we do with this? So let me just erase everything and with your permission. And eventually what we need to compute is this matrix element. Okay? And after we do it, we have to integrate over psi. But to compute this, we need to do this division into infinitesimal time steps and write it as a product. And the trick that we're going to do now is to introduce in between each of the time steps, we introduce a resolution of identity, but we keep track of the time step. Okay, so I'm introducing now an index j. Let me actually relate it to, so let's define j to be tau over d tau. Okay, so tau is the continuous variable that goes from 0 to beta in equal-space intervals d tau. So at an arbitrary tau, that is a multiple of d tau, I have an index, I have a discrete index j. Okay, so j runs from 1 to capital N, where capital N is the number of steps. Okay? So j is 1 to n. Okay, right? Well, and Yeah, and the time that corresponds to the final j equal n is just beta. Okay?
J equals beta over dt.
No, j is an index that runs from, this is j equal 1, j equal 2. Okay?
Yeah, but you define it as t, tau.
Tau is a continuous variable. Okay? Tau is a continuous variable. It's not one number. It goes from 0 to beta. So tau goes from 0 to beta, where actually beta and 0 are the same, because we actually what we want to do to compute this matrix element which is diagonal, we go back to the same point, right? But let's go to this soon. But there is a continuous variable that goes from 0 to beta. We are dividing it to dividing the axis to intervals, and we define a discrete index j that counts the steps. Okay?
Why do we want to distinguish between steps in this case?
Because I'm going to, that's exactly the thing. If I'm introducing a resolution of identity here, it's always coming with some dummy index that I'm integrating over, right? So here I'm going to have, this is the time step n minus 1, let's say. This is n minus 2, right? So I want to keep track of the different time steps, okay? Each time I introduce a different field, right? Exactly what we had last week. So this is exactly what I'm doing. I'm going to introduce in the jth time step, okay, I'm going to introduce a resolution of identity in the form of an integral over psi j of e to the minus psi j square psi j. Okay? So here I will get, here between this time step and the next one, I have, this is with psi j. To the left of the same operator, I'm going to have j plus 1, right? So let me write it explicitly, maybe with a different color. It's here between, actually, I want it to be in some arbitrary point in the middle, so maybe that's not, I think, okay, so this is what I have. This is the first, last time step, and then I have a product of many things. This is the jth term, okay? J is somewhere in between 1 and n, okay? And this resolution of identity is exactly the same form, but with now the index is j plus 1, e to the minus psi j plus 1 square, and psi j plus 1, psi j plus. Okay? Okay, this is what I get. And in these expressions, always the numbers I can always shift to the left because they are just numbers. I can put them anywhere. It's commutative. What I'm left with it, just to show you the structure, I mean, you have to really do the calculation yourself to see how I'm not going to do the algebra in a lot of details, but you already see what comes out. Of course, this I do for, again, any j between, so I have psi j is actually, let me just write here the definition. Psi j, what is psi j? It's for each j, what I call psi j is actually itself an array that has all the possible alpha indices. Okay, so I have psi j alpha 1, psi j alpha 2. Okay. Okay, but j itself is another index. So I have two indices to the field, this complex field psi, j, which is like a time index in a discrete sense, and alpha, which is some quantum number. Okay? Is it clear? So it's really a multi-component expression, but in the end it's going to be something very simple to follow. Okay? So I have here a multiple product of many things, but the main point is how I get rid of the operator. Because here I have an operator, e to the minus h beta. This is an operator. But after I introduce the resolution of identities, I'm sandwiching it between psi j and psi j plus 1. Okay? Right? So altogether, at the j step, I'm going to get okay, so I'm going to get something like this. Product, and sorry, integral over a product over j, where j runs from 1 to n, of e psi j bar psi j, where psi j again is a multiple component vector, and this little d is something like this. Okay, it's also a product over all alphas. But then what do I have inside? I have and I actually, okay, let me also do this. I introduce here. So okay, let me write it like this. But remember, I also have another integral over what I call the psi without an index. And you can think of it as simply introducing yet another j that I can call j0. J equals 0, but j equals 0, 0 and capital N are the same because we are going in our, so I erased it. In the end, we have our operator is between some psi to the same psi. It's like periodic boundary conditions. So this additional integral is actually psi of 0, which is equal to psi of n. Okay? It's both the beginning and the end of the chain. So this line is actually not a line, it's on a circle. Okay, I start at some point that I call 0, j equals 0. Then I'm dividing it to intervals, j 1, 2, 3, And then capital N goes back to the same psi.
Is it a physical thing or you're just setting
It's a mathematical
You're just setting
definition.
it like
Yeah, that's what you have. Okay. Of course, this imaginary time is not a real coordinate, but mathematically it appears in this way. Okay. Okay, so this is what I have, but what do I have inside? What I have is something that in the end, because all the operators in the end are sandwiched between some psi and another psi, I no longer have operators, I have just a product of numbers. Okay? So let me write what is the product of numbers, and the product, it's a product over J, and it's, let me write it carefully. So it's going to have, first of all, an exponential factor of, I just want to choose it convenient. Yeah, so let me choose it to be e to the minus psi j plus 1 square. This is the from the resolution of identity. Okay? Then I have expectation value of, sorry, not expectation value, a matrix element of my single step operator between psi j plus 1 and, write it, the tau psi j. And that's what I have, right? Okay. So what I'm taking into account is there is this factor, and then the matrix element between psi j and psi j plus 1. And these guys already belong to the next step. Okay. So I just have a product of all the j's from 0 to n, and this is what I have in the middle. Okay. Right? But in the end, I'll have a product of we'll see soon that this too can be written as an exponential, right, of something. And therefore, this whole thing is a product of exponentials. And when I take the product over all j, I can write it as an exponential of a sum. Okay? Is it clear? Is it clear? Don't be shy. Okay? It's a bit technical, but it's magic, because soon you'll see something very beautiful that comes out of it. Okay. Okay. So now we still reduce the problem to something that can be expressed in terms of a matrix element, but we still want to have an explicit expression for this, right? And actually, this is exactly where I use the fact that these psions are not just some states, they are coherent states. Namely, they are eigenstates of the annihilation operator. Okay? And because of that, I exactly know how to write it, because now let me introduce some general thing. Okay, so this can be erased. Okay. So, because we know, actually, I'm sorry I erased, so let me just bring it back. I have this definition and the Hermitian conjugate of it. Okay, this I have. Therefore, because of that, now let's assume that I have some operator that is normal ordered. Namely, it's a product of some A's and A daggers, but all the A's are to the right, all the A daggers are to the left. And I want to take its matrix element between some psi, let me call it psi, and some psi prime. Okay? What is it? So I know that, again, this is a product of A dagger, A dagger, A dagger, and then A's. Okay? All the A's, when they act on psi, what do they give me? Because it's an eigenstate, they're just going to give me the product of phi alphas, right? And all the A daggers, they can be thought of as if they act on the left on the psi prime. So they will give me just phi bars, right? And then I'm going to get just a complex number, which I can take outside, times the overlap of the inner product of psi and psi prime. Okay, so in other words, you can easily convince yourself, just do the exercise for a small number of operators and you'll see. You are going to get a functional of the whatever all the alpha, sorry, write it like this, of psi prime bar and of psi times psi bar psi. And well, what I mean by this is you take the operator expression for O and replace every operator by its eigenvalue, by its complex eigenvalue in the coherent state. Okay, let me give you an example. Let me actually write down a general thing. So if O is, let me write it as some product of alpha prime A daggers. Okay, this is, if you like, this is the most generic expression for a normal ordered operator. Okay? And maybe not the most generic, because you can have linear combinations of just such things, but let's just take one term, okay? Then, if this is O, then what I call O, what is this is a product over the alpha primes of, call it psi alpha prime bar, product of alpha of psi alpha. Okay? I just take the same, whatever function, I have some function of A dagger and A. Actually, let me write down a more general thing, okay? Let me write it really the most general. So suppose I have a normal ordered operator, can be written as some function of a set of A daggers times some other function of A alphas. Okay? This is an operator. It may be a horrible, it may be some exponential function, who cares, okay, whatever it is. Then this O of psi is going to be just f of the set of psi bars primes, and times f twiddle, this other function of the psi alphas. Okay? That's what it is. And this is a complex number. It's just a number, no longer operator. Okay? So we replace the operators by fields, by complex fields, and they are commutative objects. That's the advantage. Okay? There are many of them, but they are just commutative. You no longer have to keep track of the. I kept track of the order by writing this. Okay?
The only problem that we don't know exactly how they translate.
What do you mean? No, I know exactly what they are. Okay, so there are some psi's or some complex numbers that eventually you are integrating over them. Okay, you're integrating over them.
Yeah, no, what I'm meant to say that we don't really know how to it will be per psi. We don't have one general form in which O can be written using psi from A.
No, I'm saying I can. That's exactly what I'm saying. You give me an O, okay, I tell you, you have to tell me what is the function. Now, actually, we're soon seeing an example, because this is an example for a function of an operator of such of such A's and A degrees. But it's an exponential function. And, but that's the important thing, we want to keep it in normal order all the time, okay? Because of the normal ordering, we can separate, we can apply all the annihilation operators on the right, all the daggers on the left. And the result of the calculation is exactly a function. Now it's going to be some function of these complex numbers where it has exactly the form of the Hamiltonian, but you replace the operators by these complex fields. Okay, that's the idea. Okay, so let me write it down explicitly. So what I'm saying is that but notice that after I do I get this function, O of psi bar psi, but I'm still left with the inner product. But we know this inner product, right? We know explicitly how to write it. We know that it is. This is what we showed before. This is e to the psi prime bar psi, right? Where again, psi prime psi is the sum over alpha, blah blah blah. So we know what is this, and therefore I can take this. This is just application of this general identity, where my operator is now e to the minus h minus un beta. Okay? So what I'm getting from it is, first I'm going to get this inner product of psi j and psi j plus 1, which is e to the psi j plus 1 bar psi j, okay? I did this exponential factor, times the complex function expression of this. So instead of the operator h, I will now have some expression where I replace all the daggers by psi bars, psi bar j plus 1, because it's to the left, and I replace all the a's by psi j. And the same I do for the number operator. The number operator, if you remember, is just sum over alpha, Heidegger alpha, right? It's, let me write it down explicitly. It's just a total number. Okay, I write it here, and is this. So it's just one contribution to the single particle operator, and in this, and after using this this matrix element, it gives you just psi j plus 1 psi j. Okay. Sorry, I have to close everything and multiply by d tau. Right? Okay, so now let's break this thing and see what we get in the expression for, and all of this, what I wrote here, is now going to be an expression for the partition function, where I no longer have operators, I just have a product of some functions of the fields psi j. Okay? Okay, so what I'm getting, let me try to compactify it. This we can already erase. Okay. So this is what it gives. First, I'm going to get something that I call capital D, which I'll define soon. Is going to be just all the differential of all the fields. Okay, I will define it soon. Then what do I have? I have a product over all j going from 0 to n, where we also have here a constraint that psi of 0 equals psi of n. These are the periodic boundary conditions. And what we have inside of the product is, I now notice that here I want to combine this exponent and this exponent. In both of them, I have psi j plus 1 bar, right? You see? Okay, so I'm combining them and I get the following thing. You see soon why I'm combining them. Psi j plus 1 bar minus psi j right? Let me just think. No, sorry, it's okay. Sorry, it's fine. So I have yes. So I have psi j plus 1 bar. Then I have psi j plus 1. This is coming from here minus psi j, which comes from here. Okay. Writing it like this is one exponent. And then I'm left with this thing that let me, for shortcut notation, let's call this full Hamiltonian with the chemical potential. Let's just call it H grand canonical, okay? Because it's H minus mu n. Just a name for shortcut of notation. But whatever it is, it's a functional of psi j's and psi j plus 1 bars, where each of these corresponds to taking the original A dagger expression, replacing them by phi. So it's a number, it's a functional version, and I'm writing it as A grand canonical of psi j plus 1 bar, psi j, d tau. Okay? Okay. That's what I get. I get a product over J of a product of exponentials. But the product of exponential is an exponential of a sum, right? So you already start to see that I get something that if I go back to my definition, what is this index J? It's a discretization of the time steps. And if I'm taking the limit that d tau goes to 0, the continuum limit, a sum over J is going to become an integral over tau. Okay? But before that, there is one step we want, and you notice why I combine these two exponents. Because here I have the difference of psi j plus 1 and psi j. Okay? Now remember, in the end, I want to go to a continuum limit where j and j plus 1 are infinitesimal time steps that are almost the same, right? So in this continuum limit, the expression for h is now, I can actually just assume it to be local. I can neglect the difference between them. Whereas here I cannot do it because it's the small difference between j and j plus 1. And if I do this old trick of multiplying and dividing by d tau, okay, I'm allowed to do it always. You see that this will give me a time derivative. And what I'll get is something that you can express as a psi bar time derivative of psi plus something. And all that is multiplied by a d tau. Okay? So now I can go to, let me show you what I get in the continuum limit. The continuum limit, and I forgot to tell you what is this d. I will define it soon, okay, but you can imagine what it is. It's just the product over all the differential that I collected on the way. So in the continuum limit, you want to take n to infinity, the tau goes to 0. This thing, this object, will be replaced by d tau of psi. Psi j is going to be replaced by a function of a continuous variable tau. Okay? So it's now like time, really the imaginary time, a continuous variable that goes all the way from 0 to beta. And the sum over j is going to be replaced by an integral from 0 to beta. Okay? So let's see what we got from this. The final expression is going to be I first write it in a compact way, but I will define everything, okay? Altogether, I'm going to get from this object an exponential of something, or more correctly, an exponential of minus something, because I have the overall minus sign here. This something, I call an action, exactly. So it's e to the minus s of psi now psi. Well, now let me define what is this action. It is an integral from 0 to beta d tau of psi bar d tau psi. This is the term that, this is what comes from here. Plus H grand canonical, which now let me write it more explicitly. Minus mu psi bar psi. Okay, this is what it is. Where? Now, let us write some definition. What is D? So this is the action. This is what appears in the exponent. It's just an integral of something, but this something, what I denote by psi here is actually, this is a scalar product in the index with the index alpha. Okay, so remember, my psi of tau is actually an array in the basis alpha. And alpha is some, again, it's some single particle basis. For example, momentum states, okay, or spins, or angular momentum, whatever, okay?
And where did the first one, the minus psi j plus 1, like you have the derivative?
Yeah, I have the derivative, and then I have, this is psi bar j plus 1, but in the continuum limit,
It doesn't matter.
it doesn't matter, exactly. So that's exactly right. So the distinction between j and j plus 1 can be reduced to 0. The place where you cannot neglect the difference is when you have differences. Okay, right? So it's a grad, if you like, it's an expansion in gradients. Okay, so that's what you get, and now let me define. I also need to define what is D. This D is again a definition. It's going to be now the limit where when n goes to infinity, okay, of a product over all j's going from 0 to n of d psi j by j, but this on its own is also a product of this little d is itself a product over all alphas of d psi j alpha, d psi j alpha over alpha. Okay? So it's nothing but a multi-dimensional integral over many, many complex fields, which have two components. It has two indices. One is the quantum number alpha, which we choose according to a particular problem. We'll take examples next week. Actually, we're going to consider examples. And J, the index J, is a parameterization of time, which actually, when we define it like this, it goes to a continuum. Okay? So it gives us a continuum of integrals, not just multidimensional, but something like a path integral. So we integrate over all trajectories, but these are trajectories in imaginary. And the functional that we are integrating over is this object where every time I write, for example, psi bar psi, I remind you, is the sum over alpha. And this, for example, psi bar d tau psi is actually also a sum over alpha, psi alpha bar d tau psi alpha. Okay? This is the explicit expression in terms of the components, yeah?
The product over n. It's up to n minus 1.
So actually, originally we defined it starting from 1 to n, but there was another field. Remember, the outside, there was another field that we called psi of 0. Okay? So altogether, when you combine them together, you can call it, actually, since we take it to infinity, it doesn't matter. But what does matter, and that's very important, there's one thing that is very important here, it's this periodic boundary condition. So in this integral, the constraint is that these psi of taus obey periodic boundary condition. Okay, so psi of tau, this is now a function of a continuous variable, but this continuous variable goes it goes in a circle. Let me just plot. So the imaginary time is actually, this is tau. It goes from 0 to beta, but 0 and beta going back to the same place. So the time coordinate is a circle. Okay?
So it should just be a phase.
So actually, so what it means is you already see something that eventually what we get is just a multidimensional integral, and in some cases we can even solve it exactly if it's Gaussian, because we know how to solve Gaussian integrals. But here we have a time derivative, and time derivative is not convenient because it's not local in time. So what we want to do, Fourier transform. But when we do a Fourier transform, we have to notice that the functions, I'm actually integrating over all possible complex functions psi of tau, which obey this constraint, that obey periodic boundary conditions. And because of that, they're going to have a discrete set of frequencies when I do the Fourier transform. It's like basically a particle in a finite, on a circle or in a finite domain. It has quantization of frequencies. Okay? So let's see, I think we ran out of time. This is a bit heavy, but okay, we'll get back to it. But in the end, let me just summarize what we got. Basically, this is our main result, okay? This is what we got. We got an expression for a partition function, and the functional in the exponent is the analog for a many-body problem of action. Okay? It's just like, I mean, you cannot recognize it easily, but it's equivalent to what for a single particle was the Lagrangian integral of the time of the Lagrangian. But in any case, it is something in that for particular cases has a simple expression and gives us integrals that are solvable. And we can compute them and get, exact explicit functions where beta, the inverse temperature, is a parameter. Okay? Right, so this is it. This is actually our final result, and next week we're going to see how we're going to deal with it. And solve some particular examples and see how we can make progress. So one thing that I just want to say as a final note, that notice that all of this started from bosons. We do want to be able to solve similar problems for fermions. But fermions do not obey commutation relations, they obey anti-commutation. And actually, all we've done here, which assumes some complex numbers, will not work for fermions. We'll have to deal with a fundamental difficulty. Fermions are very weird objects. And they cannot be described by complex numbers in any way. Okay, you cannot have such coherent state with this being the complex number. Why? We'll see next week, I hope. Okay? But it can be done. Okay? Very good. So this is all for today, and the next lecture will be a tutorial. Yes.
את החישובים האלה לא עושים, כאילו לא עושים אנליטית, בטח אף פעם.
עושים. במקרים פשוטים, במקרים לא פשוטים עושים תורת אפרת.
אנחנו נראה את זה.
כן. נראה את זה. זה המטרה, אוקיי? זה הפורמליזם, עכשיו איך לפתור, אנחנו נראה שאפשר. אוקיי?
עובד עם ההחלטה. אם אני רוצה להתחיל...
נראה לי... כאילו...
אני חושב שזה מקליט את ההתחלה של ההרצאה של... עד הסוף, ואז הם עורכים את זה.
יופי. חשבתי, אנחנו סתם משהו מחכים, אפשר להתחיל מוקדם, אבל רוצה שיהיה בהם ההחלטה. What do you say? Start? Start? Ready? Okay. So today we're probably going to have a little bit of a shorter tutorial. We're going to go swiftly over path integral, an example for one. In your homework, you'll see another example, another method how to solve them. And in the end, we'll probably have time for it. We'll go over weak theorem, something that we missed skipped in two tutorials ago, and I saw some problems in homework with it a little bit. So yeah. Okay. One real thing that we have when we're talking about single particles in quantum mechanics, let's say I have a particle over here, I let him go, then I have like a big array of detectors on the other side, and I can, for example, find the particle after some time in another spot. Classically, we'll just say, okay, I fling the particle from one side, then you swim through like a singular path and end it on the other side. Quantum, what happens is that I let the particle here, then it sort of, the wave function, not the particle itself, sort of spread everywhere and collapse back into a single spot where I find it. But for example, I can describe a lot of different paths, for example, like this path, or this path, and so on and so forth, and all of them are valid. The only thing that happens is that we collapse the wave system in the end, the wave equation, the particle in the end. So we want to describe this process somehow. And as everything in physics, we start in a discrete and simple way. Right. Let's say the particles start in something I'll call state I. Not necessarily, I'm going to write it outside of the line because I want it. And in F. So we define quantity that are called I. And when I take this internal multiplication of these two states, get an absolute value squared, I'll get a probability to find the particles that are released in I and pilot F. But again, just a really short note, actually wrote it the other way around. We read in quantum mechanics, we always read from right to left, not left to right like normal mathematics. Now, how do I make it continuous? Well, let's just add some steps. And start with adding two slits in the middle, a very classical experiment. I'll call one A, the second one B. This will evolve my calculation up here. I'm going to keep the absolute value square on the outside for now. I'm going to evolve to F, A, I plus F, B, B, I. Basically what I'm saying is very simple. I don't know what the particle did in the middle. I just know that to get from getting to I to F, you either have to go from I to A, and then from A to F. Or you can go from I to B, from B to F. The probability for such case, will be just taking this term and giving it an absolute value squared. Now, if we give this term an absolute value squared, we'll see that we have the probability of going through A, going to I, to F, and the probability of going through B. But we also have the cross terms here. So we'll have F A I times F. Yeah, let's do it like this. F B B I with complex conjugate plus, I'm just going to make it shorter and write CC instead of writing the complex conjugate of this entire term. This will be the interference term that we know from the two-slits experiment, talking about particles. Okay, but this is hardly the continuous regime. So the first thing I can do, make it to get closer to continuous, just adding more bits, which will take this equation right here. Again, I'm writing it without the absolute value squared. I'm going to call it K. Starting xi, ending it x at the end, fine. B over n, f, n, which now n will just indicate which hole I'm passing through. Correct. This can be easily moved to continuous, but not this part. So I can add another one, another partition, another one. And there is the question over there will evolve into n 2 1 f and two. I think everything here is pretty straightforward. You probably already seen it in the tutorial, and Efrat explained the meaning of this. But I think it's very easy that if we just add more hole and more partition, we basically get the continuous term. Now, each of these state, I'm not going to write it down. I'm just going to say it like in a bit of a hand wave. Each of this, for example, this multiplication, I can take I and N1 and deconstruct them into the orthogonal basis, the same orthogonal basis, and the multiplication will be something with the amplitude of 1 and some sort of phase. So the best guess will be an exponent, and this is what we will actually have: K function, continuous K function. Okay. I'm taking everything here under the continuous. I have f I. This is kind of a squiggly end. Integrate B. Okay. Now, before I go into this equation a little bit, the action you already know, should already know. Sorry, integrate B. F another 2. But this is just action. And n, give me the n, equal to m divided by 2 pi I h bar delta t n divided by 2. And lastly, this notation for an integral x equals over dx n minus 1 x minus 2 dx one, where dxn is the endpoint and dx0 will be the starting point. Now, basically what I'm saying here is that the weight of each of these trajectory will be determined by the action, and we consider every possible trajectory, regardless if it involves the minimal action principle that you learn in classical mechanics. In fact, if you take h bar to go to 0, we'll get something here with an infinite phase, which is defined as 0 automatically. So the only term that will survive here will be the minimal action term, and then we'll get the classical solution from this equation. We only get the result of the classical solution. Yeah. I think that this is how deep we'll go through to the theory, because you saw it in class. I don't think I need to really go over it in the class again. Okay. Yeah. Let's do an example. Let's jump straight into it. All right. So first of all, if we want to solve this problem, we gotta write our action. Well, for free particle, it's pretty simple. Just as with kinetic energy. N K or N one. I divided by 12. Okay. Now, actually, before we'll do that, I want to say a little something else. We are very close. I saw that you started with the fractal bit of path integral, which is the next subject. This is almost there. Note that path integral means integrating all the possible function, all the possible trajectory that we do. And here we basically do almost the same, just very, very close to it. For each step of the way, we check, okay, what's the added phase from going here, what's the added phase from going here, then the next step. Again and again. So it's very, very similar, almost the same, but not exactly. So, still haven't learned. You will learn in the future how to actually do this sort of full path integral, full integration of functions, not of variables. But for now, we'll just try to do we'll solve this by discreting our space. Basically, we made our space continuous, and now I'm going to break it back to discrete so we can solve this normally and directly without any tricks and stuff. All right. So to break it into discrete elements, we need the first step. I think would be to break this. What does it mean, x dot in our discrete form? Well, dot just means 1 plus 1 is 10 divided by delta t, and dt will be over n delta t. Okay. And this capital dx will use the discrete discrete definition here. This is the discrete definition of capital Dx. The non-discrete is basically saying integrate over all the positive functions. Right. So writing everything discrete, we'll get in the discrete form, we'll get kappa equal n. I don't know why the convention used n when we have n so many places. x1, x2. Minus 1. Again, note that we start with 1 and then with x minus 1 because we know definitively the starting point and the end point. Right? E, I am h bar t. So this is the first derivative. The first derivative term plus the second derivative term and 1. I wrote it explicitly intentionally instead of using a sum in the exponent. Right. Now, well, now I like to argue that we can just solve this step integral by integral. Let's start with x1. I don't have any space. Right here. So, R1. Okay. Now opening these two square terms into infinity, x1, e I h bar delta t. X2 squared minus 2 x1 x2 plus 1 squared. Now I want to take only the x1 terms altogether. Get the x1 e and e bar t 2 x1 minus x0 plus x2 divided by 2 squared plus x2 minus x0 divided by 2.
פשוט שרשרת של גאוסיאנים.
You got it. This is most of physics. Just a long list of
harmonic oscillator.
Yeah, harmonic oscillator and Gaussian states. Yeah, okay. So basically we just need to integrate over this term. Let's to integrate over this term, I will just define u equal x1 minus x0 plus x2 divided by 2. And I bet you don't need me to actually solve this integral. You all probably know or can work out how to solve a Gaussian integral. Overall, we'll get this result will be square root of 1 over 2 pi I h bar delta t divided by n e to the I m divided by 2 h bar 2 delta t x2 minus x0.
Yeah. But where did the x2, x0?
This one?
No, the. Oh, okay, okay. I see how they cancel out. Okay, okay.
Okay. So too long. Okay. Basically, we got. I'm just gonna erase this k and write again the correct the new one. Okay, so we get the square root of 1 through 2 pi I bar t divided by m dx2 all the way to dn minus 1, capital N, sorry, and times e I m 2 bar t 1 over 2 x2 minus x0 plus x3 minus x2 squared plus n minus 1. Almost the same. There's a square here. Almost the same. It's a little half here, and some half outside. Right. Now I'll do the second integral, x2, and then we'll jump to the end. So it will be just 2 steps. So I mean, we're ahead of schedule, so we have time. Okay. No rush. It's all good. All right. This is enough for me. And crazy. למחוק את זה?
Yeah.
רק למחוק את הכל? למחוק את השורה הזאת כבר. And exponent. So again, the same trick of opening everything up, combining all the x2 will give us 3 divided by 2 x2 minus 1 over 3 x0 minus 2 3 squared plus over 3 x3 minus x0. Another close bracket. Right. Again, I'm gonna skip forward and tell you that all this equals to square root over 3 2 pi I h bar delta t and divided by n e to the I and divided by 2 h bar 3 delta t. And x3 minus x0 squared. You see, just like before, we basically replaced this one with a 2 and had an half. we just replaces this 2 with a 3, replace this half with a third. So let me just change this equation one more time, and then we'll jump to the third. There it is. We'll get square root of 1/2 times 2 over 3 2 pi I bar delta t divided by m square root square. Here we have an exp of 1/3 x3 x0 squared plus 4 minus 3 squared plus xn minus n minus 1. This term, square root of 1/3. I believe we can also see the pattern here. If we assume that this pattern persists, and you can check, you don't believe me, this term will just be to the power of n, n minus 1 all the time. And the term before it will be 1 over n. Lastly, in the exponent outside of the integration, we'll get x n minus x0 1 over n here. So the result will be equal to square root of n divided by 2 pi I h bar t, where capital T equals to n delta t e to the I m 2 h bar delta t, not delta, just a capital T again, f minus xi. Okay. Now, when we're doing this sort of calculation, there's a little bit of a hidden variable inside. This is all assumed that xi and xf, the transition between those two, is real. Is a real trajectory that can exist. For example, I can't break the speed of light. So what we see described here in the end about k is that if we take the probability p, the absolute value squared of this term, this phase term will disappear, and we just have an equal probability to be in every position in space in the end, but again in the normal sphere, which is described by this term here in the start, and we see that it expands with time because we have n steps and different time steps. So the more time we have, the bigger sphere that we have, and the lower the probability to be found in a very specific position. Yeah. Although you'll probably, I don't remember if we do a free particle when we do path integral, but we find a better result when we do actual path integral next tutorial. So let me know when you're ready. We'll move to the next step of the tutorial, and if we'll have time, we'll do another example that should have been in your homework. That will be in your homework unless we don't have time.
Harmonic oscillator. It's a harmonic oscillator.
Yeah. Usually we teach it in the tutorial, but Efrat actually wanted it in your homework. If you have time, we'll do it here.
Shouldn't it be like with some kind of an n power, because each one of the...
Did I erase the definition of n? I'm going to write it here. And just to make sure I'm not writing the wrong definition. And it's here. N is equal to n divided by 2 pi I bar t over 2 and yeah, that's enough.
That's after you.
So after I cancel them out, yeah. So
Did you say that the square root of propagator is a probability?
the square of this of k. Okay.
Square or absolute? Absolute value square.
P of I f equals a square. So it's small in the corner.
So just
Just
all
the-
of this without exponent and square.
Which makes sense for a free particle, you know, just bring it into space and it goes wherever you please. I'm gonna say this in like close bracket outside of the tutorial realm. This subject right here is mostly to introduce you to the math. The real like calculation, the real important results of stuff like that you'll see in the next tutorial when you do a field integral.
Yeah, because I think it's strange that we finally end up with the probability that's just a 1 over t, and it doesn't depend on initial state and final.
I would agree that it's kind of untrivial. We can talk about this a little bit more deeply after class if you want. For now, I'll basically just say math is more important than the theory. Yeah, so let's do weak theorem real quick, and then maybe we'll defy Efrat and do the harmonic oscillator instead of homework, because there's another example in homework. Right. So, weak theorem sort of brings us back to second quantization. I hope I didn't write theorem wrong. I didn't think it was. Right. First, I want to introduce you to a notation, normal order. Usually write n. For example, k, l dagger, n dagger, n. Some people use 2 dots on the other side, so 2 dots, k, l dagger, m dagger, n. Which this notation just means we take all the creation operator to the right, all the annihilation operator to the left. This all this notation means.
Wasn't this already in one of the homeworks?
It was this question wasn't was there as a bonus.
Oh.
You didn't have to do it.
Did not say it was a bonus. It just.
I did say it. I did say it in the tutorial. Over here. But anyway, I believe I did. I mean, it wasn't a long question.
No, there were like 2 separate questions that I because I had
Both of them were like. We'll touch them in a second. We'll see that both of them were like a line long.
Okay.
We'll touch them. But if we didn't do it or something, we didn't lose. I also mostly wanted to go over the subject because I saw some small mistakes here and there. So yeah. Note that this is just notation. This is not a function. I don't know if there's. I didn't try to write a function that does normal order, but as far as I'm aware, there's no like mathematical function that you or something in it and will give you normal order results. But let's either way try to do this transition from the what's in the bracket here to what I wrote in the right side, the definition.
The last one should be AM.
Right. So, AK equals, well, to organize them, I just need to use the commutator. Switch. Okay. W and W AM plus W E A W N. And then I'm just going to do it again for this term. AK W MW N plus LW LW EK MW N plus KLA and A N. This, of course, the normal order is 1. All right. Now we'll define another notation, which is the contractor. If I have two operators called A and B, the contractor between A and B, symbolizing the connection either from above or below, equal AB minus N AB, which is defined as 0 if AB normal order. This is not if AB no, AB normal order, or sig B let's do a few little examples. What is this equal to? The contractor between A dagger A.
AB. Type A dagger A. No, it's 0.
0. Right. Now for A.
0.
It's 0. Both because the commutator is 0 and also because two-dimensional operator is still in normal order.
Yeah.
And of course, we have to do one that's A dagger contractor.
As a commutator.
It's a commutator. What is it equal to? It's a real in boson.
1-1.
That means fermions would all.
In fermions, it's a bit more complicated. You need to count the transition. We'll get there in a second. We'll just touch it. I'm not gonna give it to you. We'll get there in a second. So now instead of using this commutator, you can easily replace them with just contractors. Didn't change it, right? And since this is a number, this is in normal order, this term is also in normal order with the number in the middle, I can say, I can put normal order, notation of normal order over everything here. Of course, doesn't seem like we're doing much now, but this is where the theorem kicks in. Right. So, for the statement of the theorem, we need to define a little something extra. Let's say we have a set of operator A to Z to be equal to normal order of AB to Z plus there's no all fractions. This is the start theorem. And this is the statement of the theorem. Every set of operator, I can express it as a normal order of the set plus all contractions. For example, we'll prove it in a second, but before that, let's do an example.
The factors are also normal order?
All of them are in the notation of the normal order, yes. For example, if we have A, B, C, D, the theorem tells us that we can write them as normal order, Lagrange's notation, A, B, C, D, plus, I'm going to use a different marker for this one. A, B, C, D, factor plus A, B, C, D, factor here, plus D, factor here. I'm not going to write everything because this will be, there will be a lot of terms. And different color. All the terms that have two set of contraction. So for example, A, B, C, D, where A contracted B and C contracted D, plus B, C, D, A and C, B and D, C, D, A and D, B and C. The reason I color coded them is basically for the last line, the red one. This is what we call the fully contracted terms, where there are no leftover operators. Right? Let's just look very quickly at our example for operator, cation operator. We'll see, first of all, let's try to find a fully contracted term that survives here. For example, this term. Now, AL dagger contractual is 1, and AM dagger AM is 0. And you can check the other three terms, the other three contraction term here, and see that it will also zero out. At the end, if you actually write all the terms here and calculate them, you'll see that you're only left with what you already did manually. Now, when you have for operator, of course, it's a very easy step to just organize them by manually flipping. But when you have big set of operator, this can be quicker when you try to do calculation with it, or expectation value. So before we prove the theorem, we'll see what you can do with expectation value. So let's say again we have the ABC. We want to know expectation value for it. Well, the expectation value is around the vacuum state, vacuum basis. This will be equal to the sum over fully contracted. Why is that? Well, because everything here is in the because A, B, C, D, or even more is equal to the normal order of all the possible states, and because all of them are normal order, everyone that still has an operator will have an annihilation operator on the right, the equation operator on the left, and both of them will just zero out the expectation value over the vacuum. So basically, a great tool to quickly calculate complex expectation values by basically saying, okay, which one of these many terms that we might have survives. Now let me give you just 4 quick rules on calculating expectation totals quickly. One, first, this rule, I will do them I put them in the order I usually do them when I face this kind of problem. First of all, we check if there's terms that looks this. If we have an annihilation operator at the end, equation operator at the beginning, which is practically the same, we'll have 0 anyways. 2, you want to know that the number of annihilation operator and equation operator same. Then 3, just use Fick's theorem. That's what I wrote here.
Fick's theorem will not work for an unequal number of weather operators?
You will get 0 in Fick's theorem when you do that, because if you have and there's not an equal number, you'll have an odd number of operators, and then you will never have fully contracted terms, because any contraction involves 2 operators. And if you have odd numbers of operators, you always have one extra, at least one extra. So but you don't actually have to. This use Fick's theorem is not like second. It's slower than just counting the operators, so it's a bit tough. And then there's another special rule for fermions that I always use, but I put it on the end because it's special fermion and most people don't really do fermions. Is check for bubbles in fermions. No matter where in the string of operators, if you have AA or AW, of course it's fermion, so usually we write C, but you'll forgive me this time. If in fermion we have 2 annihilation operators together or 2 creation operators together, it will always be equal to 0, no matter where they are in the string of operators. I can write C's. I can write C, C dagger, E, C dagger, C dagger, C, C dagger, whatever. And this term or this term will tell me that it absolutely zeroes out. Because this is going to be quick. If I have CC over 1, the first one will be annihilation operator over 0, cancels out, ends up 0. Of course, if there's a 0 here, it's very trivial. And if you have 2 creation operator over 0 or 1, you'll get C double 1 can equal 0 because Pauli exclusion principle. So this is an extra little thing. Let's prove the theorem. And I can erase everything. I'll go there. Okay. I love this proof because it's one of the very, very small number of proof that we can do in induction in physics. Really a math thing. So let's just, for simplicity, we define omega n to be some random set of operators. We'll start with the case of n equal 2. Omega 2 equals AB. Now, if AB is in normal order, we're done. If it's not in normal order, we can just write BA plus BB contractor. Of course, we can put an N outside of it. I didn't do anything here. This is in normal order already, and this is a number. And now that I put the notation outside, I can change the BA to the inside to AB, and we're done for n equal 2. Now, let's assume that everything works for n minus 1. Right, omega n equals A, B going to Z, equals B to Z, just omega n minus 1. The example of omega n minus 1. Right? So this term, I can write it as A times normal order B to Z plus all contractions will be equal to A times n B to Z plus A times n. I'm just going to write all. Now we have two possibilities. Either A is a creation operator, and then we're done. Or it's not a creation operator, and we need to switch it around. So let's start with this term right here. Well, that's actually the right one. So to switch it around, we'll get n b to z a plus commutator a n b z plus n all fractions a plus commutator a n all. Right? So let's start here. This commutator. Commutator A and B. Okay? Just writing it out explicitly and equals n B C then plus B commutator A and C D then plus B Y. Note that I could have that I can put it all inside into the normal order because A is not doesn't add any operators, and we know that all the other operators are already in normal order. We put everything here in normal order, and now all I'm doing is just move the commutator and adding a contractor. Then we get a contracting term inside of normal order that involves A. Now we can do this exact same step right here. with this term. I'm going to write it up because it's going to be long, but we can do the exact same process of putting n in, writing it all explicit into the normal order with the explicit commutator, replacing the commutator with the contractors, and so basically we're done. This is the entire proof. Now we have this term, which is the normal order of no contractors. This term, which is the normal order with just one contractor involving A, and this term right here, next term, is all the contractors don't involve A. The last term, the last one, which would be all the contractors that involve A plus another contraction. And I'm done. So basically, this is a proof. And I don't know if anyone here made a mistake in the homework 3 in the weak theorem, but if you did, I noted it, so you can check in your homework. Basically, we're done for today's class, and I think I'll keep the harmonic oscillator for the homework with guidance, and I'll remove a different question for you, because Efrat wanted you to do it, so you do it. That's it.
Thank you.